And so it begins. Let's start off with this. What? You have a choice of being marked tardy or being marked absent. Do something about it. All right, let's go ahead and go through this. Be careful when you put your placards down, because if you rotate it while you bring it down, it's going to record that other letter. Okay? Did I get you there? Yeah, I got everybody now. All right, so what is the answer? I got 13 of you that said 5, and 4 of you say 4. So the question is, what's the answer? The answer is 5. And that's my way of checking to see whether or not you've done the reading or not. Let's go ahead and jump into this. Okay, come on, you. There we go. So let's talk about accuracy, precision, and significant figures. Okay. Here's our measurements. Here's where we go. We're going to start out with something simple. Let's take a cylinder and measure it with a tape measure. And we measure the diameter of the cylinder to be 1.23. I take out my calculator and I calculate the diameter. What's the diameter? What does my calculator read? Do not be the one waiting for somebody else to do the answer. Be the one to go and get it yourself. One moment. There we go. Okay, should have plenty of time. What do we got? What's the answer? What does the calculator say? Keep going. I said, what does the calculator say? Okay, well, I got 3.86415557 meters. That's what I got on my calculator when I did the calculation. All right? So far, so good, right? Now, what if I took that same tape measure that I measured the diameter with, and I used it to measure the circumference? What would the tape measure read? Yes? 3.86, correct. Why? Yes? Okay, well, that's part of it, but it's actually more fundamental. Yes?
That's the limit of the measurement device, like it can't go past
Close. What you're saying is that's the limit of the tape measure. What I'm trying to get at is this. My tape measure measures down to the centimeter. That's all it is. It measures down to the centimeter, so my answer should be in centimeters. You see where we're going here? Okay, outstanding. So the circumference is 3.86 meters. What I'm trying to do, what do all these digits afterwards, the 41557, mean? What do they mean? Are they useful? No, they're not. In fact, is my measurement, is it going to be exactly 3.86? No. When I make the measurement, it's probably going to be off a little bit. And that's where we get into the concepts of precision and accuracy. Okay? The concept of accuracy, very straightforward. Accuracy is how close is a measurement to the actual value. Okay? Let's say, for example, the actual net value of a number is 2. Okay? The actual number is 2, out to however many infinite decimal places. If I make my measurement, am I going to get exactly that number? Am I going to get exactly 2? I could get 2.01. I could get 1.9998 or something like that. in order to measure, when I measure something, the accuracy is there, and I can get close to accurate, but I will never be 100% accurate. There will always be some uncertainty. Notice I'm not calling it error. It's not error, it's uncertainty. It's stuff that I don't know because I can't get it exactly to the mark. Because even if I could say, yeah, I got it exactly to the mark, yeah, did you take into account the width of the line that's marked on your instrument, for example? That would affect things, wouldn't it? The scale, reading at an angle. Okay, we've all had it before. It's called parallax error. You guys know what parallax is? Let me give you a quick little example, little activity. It's not hard at all. What I want you to do is take a finger and hold your finger up at arm's length. All right? Now, not focusing on the finger, but instead focusing on the background, take your hand and cover one eye. All right? Keeping the finger in place, take your hand and cover the other eye. What did the finger do? The finger moved, didn't it? That's parallax error because your right eye is looking at the finger at a certain angle, but your left eye is looking at the finger at a different angle. That's the reason why when you measure something with some increments on it, with some lines on it, you want to make sure that you're eye level. You're looking at it straight on. Not zeroing the instruments. In the lab on Tuesday, Thursday, I was guilty of this. Good practice is you always zero the instrument between measurements, especially digital measurements, because electronic devices, what they do is sometimes a rounding error can end up building up. Okay? So you should always zero your instrument between each measurements. Random fluctuations of heat and wind. Of course, you take a look and say, hey, the world record in the 100 meters was this. Yeah, but how much did the wind affect it? Or let's do something a little bit more physical. You measure the tire pressure of your tires before you go driving. Then you go driving for half an hour. Measure the tire pressure again. Are they going to be the same? No, they're not going to be the same because the changing environmental conditions can affect the measurement itself. The number of molecules inside the tire is still the same. Everything is still the same. The only difference is the tire is now hotter which means more pressure. That's the reason why in the driver's manual it says cold pressure. Okay, variance in manufacturing. Is every instrument going to be exactly the same? One hopes that they're very close to be the same, but there could be some variance, and there's also what's called instrument calibration. So under certain conditions, it could be off anyway. You got to watch out for that. And the ever popular, the stuff we don't know about. Stuff may come in there that we don't know about, uncounted for effects. We could try to account for them as best we can, but it could be something as simple as I didn't take into account the time it takes for the electrical current to go through the wire, because the different length of the wire gives us different times. You see where I'm going here? Okay. That's accuracy. No measurement is 100% accurate. It is physically impossible. And in fact, even when we get to the point where we could get down to 100% accurate, we get to a point we would have to get down, when we get down into the quantum realm, we get to a point where we physically can't. There's a physical rule that says we cannot ever get a 100% accurate measurement. Granted, it's down to 33 decimal places, but still, there's still some uncertainty somewhere. So no measurement is 100% accurate. We need to talk then is, what about precision? How precise is our measurements? Precision is defined as how closely a measurement can be repeated. Now, that sounds kind of a weird phrasing. So here's the way I would kind of describe it. I give you all a block of wood, and I give each of you all a metric ruler. And I tell you to measure the length of the block of wood. Is everybody going to come up with the same number? Down to, let's say my metric ruler measures down to the millimeter. Are you all going to come up to the same number? Very unlikely. Because of variance in the instruments, because of variance in the way you would interpret it, it's very unlikely. Are you all going to come with around the same number? One would hope that you come up with around the same number. Okay, so precision would be how closely around the same number you come to. Does that make sense? Okay, now we measure it. There's different ways of interpreting it. For example, the odometer in your car measures down to the 10th of a mile, right? When the odometer flips to 0.1 tenth of a mile, does that mean it's gone exactly a tenth of a mile? No, it means it's gone at least a tenth of a mile. Oh, it's even worse when you have an older car where you have the digits that roll, then it's around a tenth of a mile, right? What about pacing? Anybody who's done land nav or orienteering? Okay, for those of you who don't know, it's real simple. It's, the way it works is you take, everything is distance and direction. You take a look at your map says, okay, you need to go in that direction for so far. You need to go on a heading of 080 for a distance of 400 feet. Okay? You take out your compass, you line it up, you measure 080 as best you can, you line it up and you point in, you recognize a landmark in the distance, so that way you can walk to it, so you're not constantly looking down at the compass and bumping into things. Look at the landmark, and then you start walking. How do you measure your distance? Those of you who have had experience, pacing. You practice making your steps the same length each time. My pace is around 5 feet. I said around 5 feet, not exactly 5 feet. Big difference. There's going to be some give or take. But it's enough that if I walk a certain number of paces, I should get in the area where I can see the marker. Okay, that's if it's a amateur orienteering. If it's professional orienteering, that marker could be, about the size of a pea hidden underneath a rock or something. Okay, all right. And a meter stick, of course, a meter stick has marks every thousandth of a meter. We've got the meter, we've got the decimeters, we've got the centimeters, we've got the millimeter marks. Okay. So, what does that mean? In addition to making the measurement, we need to be aware of how much off we could be. Again, we're never going to get 100% accurate. We're never going to get, that's the exact number. What we're going to say is, that's the number, give or take a little bit. The uncertainty is the little bit. How much is the little bit? Okay? And we can reflect the precision of our measurements by significant figures. How many digits can be read directly from your instrument? So as I said before, your odometer is precise down to the tenth of a mile. Your pacing is precise to about, call it plus or minus a foot. Your meter stick, it's precise down to plus or minus a millimeter. You see where we're going here, guys? All right. Got another exercise for y'all. Okay. Work, damn you. All right, so the next exercise then, I'm sorry, I'm not going to do the exercise, I'm going to do an explanation first. How are we going to calculate that percent error? How are we going to calculate the uncertainty? We're going to measure by using a thing called percent uncertainty. Percent uncertainty, not hard to do, just takes a little bit of steps along the way. First, you make repeated measurements. Again, I give you the block of wood, I give you a bunch of different rulers, you all make the measurements, you all come up with a bunch of different numbers. What's the right number? We don't know. So we're going to assume that the right number is going to be really close to the mean. The idea being that any kind of random uncertainty, we're going to have just as much on the plus side as we are going to have on the minus side. Does that make sense? That the random uncertainty, the pluses and the minuses should cancel out. Okay? So we're going to start by finding the mean of the measurements. Then we need to find, in order to find the percent uncertainty, we need to find the range. You got a question? I'm sorry?
Yeah, so, like when I think about it, mean is all the numbers combined divided by the amount.
Correct.
When do you use the smallest number, or the biggest number minus the smallest number divided by 2 to get your uncertainty?
No, because you don't know if the biggest number or the smallest number is actually close to the mean, if that actually gets the mean. That's the reason why we take multiple readings. If we take multiple measurements and we get the mean of the multiple measurements, then we're going to get a more precise mean. If we have just the average of the high and the low, the problem is your high or low could be big outliers. So we really don't want to do that. In fact, if we recognize big outliers, we may even want to throw those out. But that's more of a lab practice more than it is a calculation. Let's assume everything is close together, though. Then in that case, we want to find the mean. We want to find the range around the mean. What that means is we take a look at each measurement and we measure how far away that measurement is from the mean. So if we have 5 measurements, then we should have 5 ranges, plus or minus. Do you see where I'm going here, guys? Okay. Then, from that, we determine what the maximum and the minimum range is. Once we determine what the maximum and minimum, what the range plus and the range minus are, we can then take that number, divide that by the mean, and that gives us the percent uncertainty. You following along with me, guys? Would it help to do an exercise? Okay, let's do an exercise then. So the exercise is, what percent uncertainty will you find for the following? 12.5 inches, 12.7 inches, 12.3 inches, or 12.4 inches. What's the percent uncertainty? Let me do something here real quick while you work on that, because I actually have the wrong number in the key, so let me fix that. What I see is 9 of you say 3%, 5 of you say 2%, 4 of you say 1%. The actual answer is, hello? There we go. Oh, there we go. The actual answer is 2%. Now, for those of you who didn't get it, let's go over that. Here's how we're going to do that. First of all, hello there. First of all, there's your numbers, 12.5, 12.7, 12.3, and 12.4 inches. The mean of that is 12.5 inches. Okay? You may have calculated a mean of 12.46 or something like that. You round it to the appropriate number of significant figures. We'll talk more about that later on. So we get 12.5 inches. Now, what are the ranges? The first number has a range of 0. The second number is plus 0.2. The third number is minus 0.2. The fourth number is minus 0.1. So therefore, your range has a maximum of plus 0.2 and the minimum, or actually the opposite range, is minus 0.2. Our uncertainty, therefore, is plus or minus 0.2 inches. All good? Now all we got to do is take that 0.2 and divide it by 12.5. And that's going to give us 0.016, and when I multiply it becomes 1.6, so I'm going to round that up to 2%. Because I only know this, I only know the uncertainty down to one place. So therefore my uncertainty percentage should be down to one place. You had a question, sir?
If you were to get the max was 0.3,
Yes, you would, and so your uncertainty gets a little bit bigger. However, really the best answer is you take multiple readings and try to see where the mean actually turns out to be. Okay, so this is not a 100% accurate idea. It's just something that it's a good rule of thumb kind of thing. It'll give you an idea of the range, the plus or minus, how much up or down you are to the ground truth. Is the actual answer 12.5 inches? No, it's not. It's close to it. We're saying that the actual answer is around 12.5 inches, more or less. Okay? Everything makes sense? And of course, the digits and the percent uncertainty depends upon the digits of the range. Now, I have another activity for you. Let's see if you've done the reading. Right? So here's the next activity. What is the sum of 75 kilometers and 250 meters? Feel free to work together on this. For you guys, 3 of you say 75,250 meters. 6 of you say 75.25 kilometers, 2 of you say 75.3 kilometers, and 6 of you are saying 75 kilometers. I wouldn't necessarily call it an even spread, but it certainly is a spread, yes? The actual answer is 75 kilometers. Now, the reason why is when is where we start talking about precision and significant figures. Okay? So let's go ahead and bring that one up, bring my lecture up, and I will explain it. When you add measurements together, you have to take into account the precision of the measurements. For example, 75 kilometers plus 250 meters. We already know that in order for us to add them together, we have to make them the like units. It's a length which will add to a length, so we can do that, but they have to be the same unit. So we're going to go ahead and convert everything into kilometers. Why will become obvious in a moment. First, we're going to convert everything into kilometers, and so we got 75 kilometers plus 0.250 kilometers. Does that make sense so far? All right. Now, I'm going to go off to the side here and stack it. So there's 75 kilometers, and there's 0.250 kilometers. And the reason why will become obvious in a moment. Let's go ahead and add them together. We get 75.250 kilometers. Okay, so let's go ahead and write that down. 75.250 kilometers. But here's where we have the issue. Let's look in the kilometers. Let's look at the 75. Is it exactly 75 kilometers? Is it exactly 75 kilometers down to the meter? No, it is not. In fact, we're not even sure about that 5. It could actually be a 4. It could be anywhere from 74.500 to 75.499. Right? That's how we would round it if we were measuring down to kilometers. So our first measurement's only good to the kilometer. Our second measurement is good to the meter. I cannot create precision. That's the big rule of thumb. I cannot create precision. So what I'm going to do is I'm going to round my answer to the column, the first column that is common to both measurements. What I mean is this. Let's take a look. I know this 7 and I know this 5, more or less. I don't know any of that there. If I take a number that I know and add to it a number I don't know, do I know the answer? I take 5 and I add to it something around 3. What's the answer? But you don't know how big the something around 3 is. So it may not even be something around 8. Okay? That's like saying if I add 5 and add to it something bigger than 3, what's the answer? Something, that's all you really know, you see? So the first digit, this 0 right here, you don't know. The second digit, the 5, you're adding an unknown to a known, which is unknown. The third digit, an unknown to a known, is unknown. The units digit, I know the 5. I've got good uncertainty about that. That is to say, it's fairly precise. And I know the 0 because it's a placeholder. So therefore, I know that number must be 5. So what I'm going to do is I'm going to go ahead and round starting from the units digit. And so therefore, my answer is going to be 75 kilometers. Now, what if instead of adding 250 meters, I added 750 meters? What would the answer be then? No. 76 kilometers. Okay? Because we could think in terms of rounding, right? 750 meters is close to 1 kilometer, so it's very likely that I'll actually bump up the actual number up. But this is a case where the precision of the second measurement is within the precision of the first measurement. So we really can't tell. That's basically like how much bigger am I if an ant starts crawling on my head? Not any real change, is it? because the ant is not significantly large enough compared to me. Okay, I've got another exercise for you. All right, here's the next exercise. What is 3.75 centimeters times 1.453 centimeters? Mm-hmm. 75 centimeters. Again, feel free to discuss. Help your buddies out. Okay? Oh, I can't get you there. Solomon, your finger's in the way. There we go. Gotcha. Excuse me? Sorry. Okay. Okay. Where's Tyler? Okay, got you here. Well, here's something interesting. I got 16 that say D, I've got one that says B, and one that says C. So, anybody want to change their answer? Just go ahead and put your placard up if you want to change your answer. Hello, there we go. Anybody else? Hint, hint. Okay. You missed out on the opportunity because the answer is 17. 17 of you got correct, which was the 5.45 square centimeters. One person said 5.4488. I'm going to make a guess here that since B and D are on opposite sides on the placard, you probably got it upside down. So make sure you check it next time, okay? So anyway, the answer is 5.45 square centimeters. So let's talk about that. Okay, when we multiply measurements together, again, we cannot create precision. What is 3.75 centimeters times 1.453 centimeters? Well, first of all, our units of measure are going to be square centimeters, because centimeters times centimeters are going to give us square centimeters. Our answer, when we plug it in the calculator, is 5.44875 square centimeters. But again, I cannot create precision. There's a limit to my precision. My first number is good to 1 part in 400. Do you understand that statement? Does that make sense? Good to 1 part in 400. That's the uncertainty. The second measurement is more precise. It's good to 1 part in 1500. So my uncertainty is much less in the second measurement than it is in the first measurement. Well, that kind of makes sense, right? But my calculation turns out the uncertainty becomes 1 to 1 part in 500,000. That does not make any sense. Do you see what I've done here? We've gotten rid of uncertainty, and we can't get rid of uncertainty, not this way. Okay, so what do? We have to get this uncertainty for my answer to be close to the least precise measurement, the uncertainty of the least precise measurement, which happens to be the first one. So the rule of thumb is the number of significant figures in the least precise measurement. So that means the first number, which is only good to 3 significant figures, we're going to use that, so it becomes 5.45 square centimeters. Okay? Now, there certainly is, when you get up to higher level science and stats, there are certainly ways of measuring this uncertainty more precisely. That's where the plus or minus comes into play. But for right now, we'll just use the significant figures in order to carry over the precision, okay? Speaking of significant figures, what are they? Significant figures are the numbers that you would actually read off of your instrument. That's my rule of thumb. Significant figures are the numbers you read off of the instrument, or when you do your calculations, the numbers that you should read off of an instrument with the same precision. Does that make sense? So that means that non-zero digits are significant. Let's take a look, for example, when I was measuring the pennies. They were around 3 or 2, right? Those are numbers you could read directly off. Those are measurements. So non-zero digits are significant. Zeros between non-zero numbers are also significant. So if I had a number like 405, that 0 could have been a 1, it could have been a 2, it just happened to be bigger than 400 and less than 410. So those are significant. Digits following a decimal place, zeros to the right of the, let me read it then. Zeros after significant figures that are to the right of a decimal point are significant. Let me give you an example here. I have here a 2-meter stick. My 2-meter stick in the right in the middle says 100 centimeters. Or I could write it as 1 meter, right? Halfway through the 2-meter stick should be. But how precise is it? It's 1.000 meters. Is it possible that I could actually read that particular number on this meter stick down to the millimeter? Yeah, I could put somebody right up against there and read 1.000 because it would be less than 1.001 but greater than 0.999. You see what I mean? So, trailing zeros after the decimal point are significant. It means we could have read a number at that spot. What about leading zeros? No. Leading zeros before or after the decimal point are always placeholders. Okay? Leading zeros are always placeholders. So let's go ahead and do a little exercise. This is not going to be a Plicker's exercise. Let's go through this. How many significant figures are in each of these numbers? In this number, how many significant figures are there? 4, correct. How many significant figures in this number? 4, correct. How many significant figures in this number? 5, correct, because the trailing zero after the decimal point means I could have read a number there. How many significant figures in this number? I've got $1,200 in my pocket. How many bills do I have? I've got $1,200 in my pocket. How many bills do I have? Do I have hundreds, tens, or singles? In each case, I could have $1,200, correct? You do not know the precision because you don't know what the smallest unit of measure is that I can measure here. Do you see where I'm going here? We do not know the answer in this case. We do not know if we're good to the tens unit, the ones unit, or the hundreds unit. Now we're going to get a little bit confused here, aren't we? Right? Is there a way around it using the rules of our significant figures? Yes?
So it's not too simple.
It is not. I don't know. Again, if that's $1,200, I don't know if I'm carrying hundreds, tens, or ones. Yes? If I put a decimal point at the end, it would say 1,200 point. That would mean the 2 zeros would be significant, right? But what if I'm carrying hundreds? I've created a precision that doesn't actually exist by putting the decimal point artificially. Do you see what I mean? So we can't do that. Yes? What's that called? Scientific notation is our answer. The reason why scientific notation is our answer because the first digit is always a non-zero number. In scientific notation, our first number is always a non-zero, first digit is always a non-zero number, and it's followed by a decimal point, which means all the numbers after it are going to be significant. Does that make sense? So by using scientific notation, my number 1,200 turns into 1.20, in this example, by the way, turns into 1.20 times 10 to the third. How many significant figures in that number? 3, and that solves our problem. If I happen to have tens, that would be the correct. If I happen to have hundreds, 1.2 times 10 to the third. If it was singles, 1.200 times 10 to the third. You see how that clears that up? So scientific notation goes a long way to helping. By the way, two things. Number one, please notice that on the bottom line, it says 1.20E3. Those of you who've worked with Excel spreadsheets know that's how you enter a number in scientific notation into a cell. This also is the format to enter a number in scientific notation into WebAssign. So if your number turns out to be something really, really big, like the mass of an electron, really small, 9.11 times 10 to the minus 31 kilograms, you would write that 9.11e minus 31, and the computer will recognize it that way. However, in publications and in writing, you want to write 1.20 times 10 to the third, because that's the proper notation. You see where we're going here? That's stylistically. You had a question?
So on a test, if you gave us a number like 12,000, how would you know how many secrets around?
That's a good question. Well, that depends on the question, isn't it? Depends on the question I ask on if I give that number there. Now, having said that, here's a little bit of an aside. In general, in WebAssign, as a rule of thumb, use 3 significant figures. The reason why is because WebAssign will count correct any answer that is within 1% of the actual value. Okay? Any number that is 1% of the actual value, WebAssign will count correct. If you put in only 2 significant figures, your precision could be as much as plus or minus 6%. You following along? So even though you've got the right number and you rounded it to the right, if you rounded it to the proper number, if the answer is 12 that you write down, but the answer is supposed to be 11.6, okay? What's 1% of 11.6? 0.1. Do you see where I'm going here, guys? And so it would accept as an actual answer 11.5 to 11.7. But if you put in 12, because it rounds, then you're outside of the range and WebAssign is going to count it wrong. You see where we're going here? So for WebAssign, unless it says specifically on significant figures, or you see changes in significant figures like 4 or 5 digits, go ahead and assume 3 significant figures for your answers, okay? Okay, that gets around the 1% limitation. Okay, any other questions? Any answers? Okay, wow, I got done 10 minutes early. That'd be a good day, isn't it? Especially for a Friday. So,